Okay, so now we just want to continue with this derivation of the black body radiation. As you remember, black body radiation was a special case where you had no reflection. And one way you could make a black body device right here, a device that emits black body radiation, is with a cavity. And if you heat up this cavity and the atoms are jiggling here, creating my light, all the light that's coming out of here, very little of it is what went into it right there, because any light going in would probably just die out inside here. So this is all light that was emitted off the surface. So this is what we call a black body. And black body radiation gives me an exact spectra that's independent of the material. And remember, what we're plotting on this axis is J of Ft. It means J was just a function of frequency and temperature. It's a power per unit area, so that's what we got up here, but it was normally per frequency. Now if we multiply it by dF, then this is really what we're plotting out is the area right here. And so this J of Ft dF, the whole thing, is the power per unit area emitted between F and F plus dF, or if we could put it in terms of wavelength, it'd be wavelength and wavelength plus d wavelength. We could write it either way because we knew there was a relationship between frequency and wavelength. Okay, and we had two rules here that fit. As you get hotter and hotter, this peak shifts this way, and the peak wavelength times the temperature was a constant. So at twice the temperature, the peak wavelength would be cut in half. And this second one was, if we integrate this, add this all up right here, it came out to be sigma t to the fourth, which was Stefan's Boltzmann constant right there, and this is Stefan's law right here. Okay, so now we're going to say two people, Raleigh, E-I-G-H, and Jeans, just before the 1900s, took a crack at this derivation. So how do you try to derive this radiation coming off this spectra? That's what we want to derive right here. Well, they said, instead of working with this J, this power per unit area that's coming out of here, instead of working with that, it might be better to work with the energy per volume inside. So what we're going to do is we're going to look at energy per volume over a little frequency range. So we're going to call this mu right here. And this is going to be my energy per volume per hertz. But if I multiply it by a dF right here, then this whole thing is just in energy. Sorry. This is going to give me the energy per volume between F and F plus dF right here. This is between F and F plus dF. So inside of here, it's all the energy in here divided by the volume in here. And the two should be related. This should be related to this, because if I make the energy, more energy in here, let's say I double the energy per volume, I'm probably going to double the amount of power that comes out the area right here. The two are related. That is, J sub F T dF should be related to mu right here. I don't know, proportional. right here. So let's just say proportional. Well, let's just give it a constant. Let's say it's A. We'll figure that constant out, times mu of F T dF. I just want to get that constant. I'd rather work, why would you rather work with energy and not with power coming out of the end? Well, there's something in thermodynamics called the equal partition of energy. The equal partition of energy says when you're in equilibrium, an equal amount of energy is associated with each energy state that's inside there, which is more or less another way of saying energy is shared equally among everything in there. So that's why they'd rather use the energy. So now how do I get that proportionality constant? Well, suppose we look at this part of it right there. I'm just going to blow that part region up right here. I'll make this on the bottom of my picture right here. So here's that opening. I just moved it to the bottom right there. And this has some area, I'll just call it delta A. It's the area of my cavity. And out here, I've got, let me just put a line right here. Out here, we've got a little bit of a volume right here, a little piece of volume right here. Now remember, this right here is an energy per volume. Mu dF is an energy, we'll leave that out because that'll just keep going all the way through. So mu dF is an energy per volume. Energy per volume. So the amount of energy in that little piece is, just move that over to this side, and we'll call this just dV right here. So the amount of energy in this box right here, this little box, energy, I guess it'd be dE since it's in an infinitesimal box. That little infinitesimal amount of energy is mu dF times dV right there. So there's how much energy is in this little box right there, this little infinitesimal box. Okay. So what are the odds? I have to equate the energy in here with what comes out, the power leaving right here. What fraction of that energy is going to get out through that hole right there? Well, you notice if this were a sphere, let's say this were a big sphere, and you had a little hole here in it right there, delta A, and you were and that little piece was in the middle. Let's just say it's in the middle of the sphere of some radius r. Well, if you were standing in there, wouldn't you say, well, it's dark in here except I see a little opening right there? Wouldn't the fraction of this energy that gets out is just the fraction of that little area to the entire area? So I see a little opening and I want to know what's the odds that part of me is going to go through there. It'd just be the ratio of those two areas. It'd be the ratio of delta A to the full area. The area of a full sphere is 4 pi r squared. So that's what it would be if I was in the middle of the sphere. But what happens if I'm way over here, not near the, I'm over here. Here I'm not in the middle of the sphere. Middle of the sphere would be over here. Well, you notice what happens to the size of the opening. The sphere still is a sphere, even when you're there. It's dark everywhere except for a little hole. But the opening gets smaller because I notice when I look at the opening this way, say the opening is the size of the page. But now, as I get off to the edge of it, the size of it looks smaller and smaller right here. As a matter of fact, if I look at it edge on, if you get way over here, you barely even notice that hole right here. And the size of it just goes as the cosine of this angle right here. If we just put this theta right here, why? When theta is 0, you see most of the area. As theta gets bigger, when you get way over here, cosine of 90 is 0. The hole looks really small right there. So if you're off-center, which we are over here, it should be dA cosine theta. Okay, so if this is the energy in there, if I want to know what fraction of this energy is going to get out through the hole, it should just be this times the probability that I get out right here. So the fraction that exits, fraction of the energy that exits the hole, should just be this mu df dv times the probability, delta A cos theta over 4 pi r squared. Delta A cosine theta all over 4 pi r squared. Okay, so all I have to do is now, since this is how much of that gets out, I just have to add it up for all the pieces in there, and that'll give me the total that comes out versus what was inside. So I have to just integrate this over all of the space in there. Now I don't want to use rectangular coordinates. Rectangular coordinates are a lot more difficult to use. I'm going to use polar coordinates. Now just to remind you of polar coordinates, right here, what do you have? You have r, you have theta coming down from the z-axis, and then you got phi that goes around. There's the x and there's the y right there. So we have a little volume up here, a little volume. This dimension right there would be, if that's r, this dimension would be dr right there. Then we have a little dimension this way, right here. Well, if this is theta going down to here, this little angle would be d theta. And so this arc length would just be r d theta. So this dimension is r d theta. Okay, and then we just need to come around this way, a little amount. Well, if you bring this down right here, the next piece down, it looks something like that. This length, since this is r, if you make a little triangle right here, this is r cosine theta, this is r sine theta, and this would be delta phi, or d phi. So this dimension, this third dimension would be r sine theta d phi. So this little cube, it's kind of a cube, it'd be this times this times this. That's what dv is. Go back and look at your math book. I think they must do that in calculus, I think 1C. So that little dv in spherical coordinates is this times this times this. So it's r squared sine theta dr d theta d phi. Okay, so now we'll just put that right up into here. And so now we get the fraction that leaves. We'll put that up in there. So we got mu df. Then we got all of this right here. But you'll notice the r squared and the r squareds drop out. So I don't have that. But I still have the sine theta. I got a cosine theta. I get a delta A. I get a 4 pi. And we also get the dr, d theta, and d phi. Okay, so there is, again, the fraction that leaves out of here. Now I'm just going to add them up for all the pieces. So I just have to integrate that. So the total amount of energy that exits the hole So this would now be the total energy exiting the hole, I just have to add these all up and I integrate it right here, but I can bring out whatever's constant. Well, what's constant here that can be brought out? Well, mu and df have nothing to do. They're the same here as they are there, which is, it's mu, all that's the same. dA is a constant and 4 pi is a constant. So I'll bring all that out in front. So we got mu, which is a function of frequency and temperature, df. We can pull out the delta A. We can pull out the 4 pi. And all I have to do is integrate the other three terms. So we have to integrate over dr. We have to integrate over d phi. And we have to integrate over d theta. And we still have a sine theta and a cos theta. Sine theta and a cos theta. Now, what's the limits of integration? Well, from over here, theta is just going to here. You're outside the cavity here. So it's just going from 0 to pi over 2. So this goes from 0 to pi over 2. The phi, which goes around this way, is going from 0 to 2 pi. It goes all the way around. So that goes from 0 to 2 pi. And the last one is r. R is going to go from 0 all the way out to, well, you notice since the light coming, this is light coming toward here, we know that the speed of light is c, which is the distance r over delta t, where delta t is how much time it took to get there. So we could just call r just c delta t, where delta t is just the time it took to get there. I'd rather put it like that. So this is just going to go from 0 to c delta t. Okay, well, now these integrals should be pretty easy to solve. We can see that this integral is just d phi from 0 to 2 pi. This is just 2 pi. This is just dr from 0 to c delta t. That's just r, which is c delta t. C delta t. And then this one, that's just u du. So that's just sine squared over 2 evaluated. So the sine squared here is just 1 minus 0, which is 1 divided by 2. So this is just 1/2 right here. So that's why I said these were easy integrals right here. Okay, so what all cancels out right here? Well, it looks like this 2 and that 2 cancel. This pi and that pi cancels. And so this becomes, oops, I want to be in black. This becomes mu of frequency temperature df times delta A times c delta t all over 4. Okay, this is the total energy right here, but I want to compare it to J. Remember what J was? J is the power first per unit area that's exiting. Well, if I wanted to turn this into, this was energy, total energy leaving. If I wanted to turn it into power, I divide it by delta T. So I'm going to take this delta T and put it down below over here. Now this is a power. And if I take this delta A and bring it down below, then it's the power per unit area. That is my J. So it looks like J of frequency and temperature, df, what we had before, is just, what, C over 4 times mu. F T df. So there was my constant. It's just a factor of C over 4 in there. Okay. So now we're going to work with this right here. We're going to work with that term. Once we solve that, then we can plug it in and we multiply by C over 4 and we get our J right here. So how do we get this term? Now we're going to work with that term right here. So again, this is the energy per volume. So mu F T dF is the energy per volume. Okay, so what I'm going to do is within a little range between F and F plus dF right here. Well, remember, what's creating this energy are these oscillators on the wall right here. And so what I'm going to do is, the more oscillators you have on the wall, the more energy you have. So what I'm going to do is I'm just going to break this energy into the number of oscillators at a certain frequency between F and F plus dF right here. So this is just how many oscillators you have at each frequency times, remember this has got to be an energy, times the average energy of those oscillators. The number of oscillators times the average energy gives me the energy right there, and then divided by the volume. Okay, so now I just broke it up into smaller pieces right here. I just need to calculate what this is, what that is, and what that is over there. Now, when they said if we just wanted to calculate how many oscillators you have per volume, first of all, let's make the volume nice and easy. A cube, L by L by L. L by L by L going this way. So that's going to be easy. That's just going to make it L cubed. Now, they also said, let's make this a metallic box right here, made out of a metal right here. Why? Because, in what you learn in electromagnetism, that electric field is always zero on the conductor right here. So what that's going to look like is when you look at the waves in here, the waves have to have a node on the ends. So it's either going to be like this, or it has to be like this, or the waves have got to be like that. You've got to have what's called standing waves. Standing waves. This is what you'd get if you just pluck a guitar string, you'd see standing waves on it. You'd actually see them all there. This is what you get in a microwave oven. You get standing waves but just one frequency right there. And so that mean that the length from here to here has got to either be, that length is either going to have to be a half a wavelength, or half a wavelength, or a whole wavelength like this second one, or 1.5 wavelengths, or 2 wavelengths, and so on, or just n wavelength all over 2. Okay, so now if you just, normally I used to derive and add them all up, but I'm just going to give you the result. When you add up all of them, right here, all of them, not only do you have to add them up this way, but you got to add them up this way, and you got to look at the polarization, because you could be like that and you could be like this, so you'd have to double it for the polarization right here. But what you're going to get for this term right there, when you add them all up, you're going to get N F T dF is equal to 8 pi F squared L cubed dF all over C cubed. So that's because, and what this says is at higher frequencies, you have more possibilities. Well, that's because the wavelength is smaller. If the wavelength gets really small, you got a lot of possibilities in here. So this is this term. And the reason why I also didn't derive it is because it doesn't come out, it doesn't matter that much in my argument right here. Okay. So you notice that this L cubed and that L cubed cancel. So since those L's cancel, this just becomes this just becomes 8 pi f squared, 8 pi f squared. The L cubes drop out all over C cubed times the average energy. And we have a df, that df, I don't want to, oh, he's right there, times the df. Okay. Then when we want to convert it vectorally, when we want to go all the way back to here, J will multiply it by C over 4 right here. So that means that this term right here, if we plug that all up into here, we're going to multiply it by C over 4. If you multiply this by C over 4, this becomes a 2 pi f squared average energy df all over C, one of the C's there gives me a C squared. Okay, so now I just need to get the average energy. That's the last thing I need to get. So how do we get that right there? Well, how do you get the average of anything right there? The average of anything. I mean, let's just say I have some numbers here. How about if I have, say, 1, 1, 1, 1, 2, 3, 3, 2, well, let's just say 4, 4, 5. Let's just say we want to find the average of those numbers right there. So what do? You add them up and divide by how many there are. That's how you find the average of numbers. But you don't get on a calculator and go 1 plus 1 plus 1 plus 1. Hopefully you're not doing that on a calculator. Which you could, at least to simplify, you could say, how many ones do I have? Let's just say the number of ones, I have 4 of them, times 1. Plus the number of twos times 2. Plus the number of threes times 3. Plus ... You could do it like that. That would be like the sum of all of them, divided by how many numbers there are. That would be the number of ones, plus the number of twos, plus the number of threes, plus ... So it looks like a definition of the average is the sum of the number of number sub I, say, times I all over the sum of the number of i's, right there. I goes from 1 to as many as you have. But these were discrete. These are integers. What if you had real numbers instead? If these were real numbers and decimals right here, well, then you'd probably turn, instead of having that being a sum, you'd probably turn that into an integral, and you'd probably write this as the integral of, and you'd say the distribution of numbers, the distribution of x times the x value, dx, all over the integral of the distribution of x, dx. This is exactly the way you find the center of mass in classical mechanics. The center of mass for a continuous object is how the mass is distributed times x over how that's distributed right here. So that's what we want to do for our energy. We want to, for our average energy, we just need to integrate how the energies are distributed, dE from 0 to infinity, all over the integral from 0 to infinity of how they're distributed, dE. Oh, this one has an extra E in it right here. DE. Okay, so that's what we have to do. But we have to figure out how are the energies distributed right here? How do you distribute energies inside that cavity? There's a special way that things are distributed. I mean, let me just digress for a minute. Maybe I'll just digress right here. Suppose we have a box right here. Just to make life really simple, let's say we have 4 items in there, four entities. Entities. They could be, let's just say they're springs. Something that has energy, springs. Okay? And they can exchange energy, and I'll label them A, B, C, and D. 4 springs. A, B, C, and D. 4 springs. And they can give each spring, they can give it to the energy to another object right here. Just like in our cavity, that light can hit the wall and it can move the energy around right here. So they can exchange energy. Exchange energy. But it's fixed within the box right there. And then let's assume, just for now, let's assume that the energies are restricted. We'll just say the energies are restricted to 0. Each of the springs can either be 0 or it can be delta E, or it can be 2 delta E, or it can be 3 delta E, and so on. And later I'll just let delta E go to 0, real small, so it's more continuous. But right now it's discrete right here. And let's assume that the total energy in here, the total energy is 3 delta E. So there's how much energy we have. So how do these springs behave then in here? Well, suppose we'll come over to here. We're going to make a little boxes here for a minute. How many? This is going to be E equals 0. E equals delta E. Delta E. This is 2 delta E. This is 3 delta E. And now I say, how can I distribute these springs into these boxes so that it fits all this right here? Well, it could be that since the total energy is 3 delta E and I have 4 springs, maybe one spring is hogging all the energy and the other 3 springs don't get any. Right there. That's one possibility that we have in there. Another possibility is, let me just draw this again here. Another possibility is one of them has 2 delta E and one of them has 1 delta E, that would add up to 3 delta E, and the rest of them don't have any. Okay, and I think there's one more possibility. That I could have 3 of them right here and 1 of them there. That's the only possibilities that these can have right here. Now, you might say, well, how many combinations can you have like this? Well, spring A could be up there, or spring B could be up there, or spring C, or spring D. So there's 4 possibilities on this case right there. Likewise, on this one, spring A could be here and the rest could be there, or spring B could be there and the rest, and spring C and spring D. So there's 4 of these too. Over here, spring A could be there, B, C, or D. There's 4. Out of the 3 that are left, the 3 could be over here, and then whoever's left has got to be down here. So it's really 4 times 3, which is 12. So those, it looks like the total number of possible combinations are the sum of these three. So there's 20 different orientations for all these springs. And so the probability that you're in this configuration would be 4/20ths, because there's 4 out of 20. This one would be 12 out of 20. This one would be 4 out of 20. So now if we ask what's the expected amount in this box right here, in the E equals 0 box? What's the expected amount in 0 energy right here? Well, I've got 3 of them here with a probability of 4/20ths, plus 2 of them with a probability of 12/20ths, plus 1 of them with a probability of 4/20ths. Well, if I multiply all this out, this is 12 and 24, that's 36, and 4 more, that's 40 over 20, which is 2. On average, I should see 2 in this box. Well, that looks pretty good, because it looks like on average I do see 2 in that box right there. How many do I expect to see out of this box, delta E? How many do I expect to see? Well, I got 0 times 4/20ths. You got 1 times 12/20ths. So you got 1 times 12/20ths plus 3 times 4/20ths, which is 12 and 24/20ths, which is 12/10ths or 1.2. So I should see on average maybe 1.2 in this second box right there. What about the next one? N in at 2 delta E. Well, I only get 1 right there. 1 times 12/20ths. Is that right? 1 times 12/20ths. What did we say for this one right here? Did we get that one right? That was 1 times 12/20ths plus 3 times, I just wanted to get that 12/20ths, which is 24/20ths. Okay. And this one right here gave me 1 times 12/20ths. 1 times 12/20ths. It should be half as much. 1 times 12/20ths. Oh, that's 6/10ths or 0.6. 0.6. And the last one up here would just be 1 times 4/20ths, which is 2/10ths, which is 0.2. So if you were to plot this out, this is the energy right here, energy. This is what I expect to get the distribution of it, delta E. You notice when E was 0, when you're way over here, it was 2. Then when you get 1 point at delta E right there, it was 1.2. At 2 delta E, it was 0.6. At 3 delta E, it was 0.6. Sorry, that was 0.6. This is down to 0.2. Well, if it was continuous, you would just get a curve that looks something like this. This has a special curve to it right here. This is called a Boltzmann distribution. Boltzmann distribution. And it follows a specific equation right here. This is just e to the minus e over kt. It's an exponential right there. Comes up a lot of places. Just the gas in this room follows this distribution where E, you'd put the kinetic energy, 1/2 mv squared. So our distribution right here that we're going to use is going to be e to the minus e over kt. Okay, and so once we plug that in and integrate, which we'll do on the next video, we should be able to get our delta, our average energy, plug it into here, and hopefully this derives the whole spectrum that we want. And so we'll just continue this on in the next lecture.